Alright, so in this video, we're going to be talking about the equation of a line in 3 dimensions, okay? So, ever since algebra, we've been working with the equation for a line in 2 dimensions, and now we're bumping it up to 3 dimensions, okay? And, well, how do we find the equation for a line in 2 dimensions? Well, we found that equation for a line in 2 dimensions by using a point on the line, okay? A point on the line and the direction on the line. Okay, and that was the slope, right? So, for example, in 2 dimensions, our equation was y equals mx plus b. Okay, and we could find this equation. We could actually solve and figure out this equation using the direction. Okay, the direction. We find that with the slope. Okay, and if we knew a point on the line, well then we could know x and y, okay, and that would give us b. Okay, so I guess I could kind of write like this. Okay, that would give us our b. All right, now in 3 dimensions, what does a line look like in 3 dimensions? Well, it's going to look something like this. Our line is going to be L here, okay? And what I have here is I have position vectors for 2 points on the line, okay? And a position vector is basically just, it's pointing out the position of a point, okay? It's pointing at the position of a point. So for this R0 vector, okay, or R sub 0, however you want to say it, I'm going to say R0. It's just starting at the origin and it's pointing to the position of that point at the end of R0, which is the point x0, y0, z0. All right. Now, we also have another vector, okay, just going to some random point x, y, z. Okay. For R0, this is the point that we know. Okay. This is now the red, I guess you could say, the point on the line. All right. Now we also need the direction. Okay, we have a point, we need the direction. Okay, and we're going from this point x0, y0, z0 to this point x, y, z. All right, and the vector going from that point to this point is vector A. All right, but what we're going to do is we're going to describe vector A as vector V, okay? Vector V is going to be giving the direction, okay? And we're going to be multiplying it by a parameter t, okay? So we're going to have vector V times t, okay? Why do we have something like that? Well, why do we need a parameter? Well, vector V is not necessarily always going to be the same length as vector A. Okay, so we need this scalar multiple to make this vector the same length as this vector. All right, so let's actually show you what this equation looks like. Okay, now I'm going to write this out again, but this time I'm going to write it as y equals b plus mx. Okay, as we kind of said before, the point on the line is giving us b. All right. And the direction on the line is m, all right? Well, now in 3 dimensions, what this equation ends up being is that r, okay? So if you're trying to find a point on the line, that's going to be determined by r, okay? That's the position vector for any random point, okay? That's going to be equal to this vector r0 plus, now you're going to have your slope, all right? And that's going to be represented by, you're going to have a TV right here. Okay? A T times vector V. All right? So you can kind of see now that you have a point that you know, all right? And you have a direction, and that's being represented by vector V. So you can kind of see the parallel here between 2 dimensions and 3 dimensions, okay? So that's kind of the comparison that you need to see. all right? And this equation right here, because it has vectors in it, that's how you can remember it. This one is called the vector equation of a line. Now my hopes with this is that this isn't going to be something that you have to remember, because you already can see the parallel between 2 dimensions and 3 dimensions, okay? So you can just do this yourself if you're ever not sure, okay? You set up your initial point and you put it where the B is, right? Then you have your vector, right? That's representing direction, and that goes right where your slope goes, okay? And the only difference now is you have to multiply it by a parameter, okay? And that's going to equal whatever point on the line you want. So that's kind of the idea here. So there are 2 other equations for a line in 3D, and these are also really equations that you don't necessarily have to remember, because you can find them using the vector equation. Okay, so first we got to understand that each value of t is going to give us a position vector. Okay, it's going to give us a position vector when you do all this piece right here, the vector r naught plus the parameter t times the vector v, you get another point on the line. That's the whole idea. Okay, and so what we can do here is, if we start to actually do this out, we can get another equation. Now we know that vector r is x, y, z. All right, vector r naught is our initial point, our point that we know. Okay, that's x naught, y naught, z naught. And we're going to also add t times our vector v, which is going to be represented as a, b, c. Now watch what happens if we start to actually do this out, okay? We get x, y, z equals, let's just do a scalar multiplication here. Let's multiply this t through. Okay, this is something that we know how to do. All right, we get still x naught, y naught, z naught. This is going to be plus the vector at, comma bt, comma ct. Okay, so all we did was multiply that t through. Let's do another step. Let's do some vector addition. Okay, if we add these 2 vectors, what we get is another vector that is basically x naught plus at, comma y naught plus bt, comma z naught plus ct. Okay, this is just vector addition. All right, and we're almost done here. Really what you have to see here is that your x component on this side equals your x component here, right? Your y component on this side equals your y component here, and your z component on this side will be your z component here. So what we do is we can set these all equal to each other. We have x equal x naught plus at. Okay, we have y equals y naught plus bt, and we have that z equals z naught plus ct. And these are our parametric equations for a line in 3 dimensions. Okay, so all we did was we actually just started to compute this formula out, and literally that's what we get. Okay, so we just get an individual equation for each component, for our x, for our y, and for our z. Okay, and to get the last equation, all we have to do is eliminate the parameter. Okay, there's a t in each one of these equations, so let's solve for t. Okay, if we solve for t here, we get that, well, let's start out here. If we subtract an x naught on both sides, we get an x minus x naught equals at. All right, and then let's just divide a on both sides. So you can see that x minus x naught over a is going to equal t. Okay, and so I don't bore you, you can kind of understand that this is going to be the same exact thing for this and this equation. So really, we get our next pair of equations by setting all of them equal to each other, because they're all now going to be equal to t. We get that x minus x naught over a equals y minus y naught over b equals z minus z naught over c, and this is our final type of equation called the symmetric equation. Now you can also easily kind of pair up the name of the equation to the equation itself because, well, the vector equation has vectors in it. The parametric equations, well, they are parametric equations, right? You know, when we dealt with parametric equations in Calc 2, we had an equation for x, an equation for y, and like that. And for our symmetric equations, well, these things are equal. That you can kind of think of as, oh, they're symmetric, right? Stuff like that. So, anyways, as closing remarks here, I wanted to just mention quick how I think I really messed up with equations of lines, and we're also going to do planes later on. I tried to remember. I just tried to like remember all these equations, and I think that was really bad because I didn't just understand how we got the equations. I just tried to remember them and call it good. Okay, and while you can get away with doing stuff like that sometime, it really didn't work for me with this topic. Okay, so you know what I recommend is just kind of understanding the whole process from one equation to the next. Okay, you don't have to remember the parametric equations, the symmetric equations. Okay, if you kind of understand how we get to the vector equation from the 2D line equation, then you're really set. Okay, you can find the parametric equations by now doing out the vector equation. Okay, you know that vector r is representing this vector x, y, z. You know that r naught is representing this vector of the point that we know. Okay, that's x naught, y naught, z naught. Okay, and you know our parameter t, that's just going to stay there. And our vector v, that's going to be represented by a, b, c. All right, and then you go out through that, you get your parametric equations, okay, and then you just eliminate the parameter. And that's how you get your symmetric equations, okay? So this is all stuff that we've kind of dealt with before. So, you know, understand the process. Don't try to just memorize all this, okay? Because I guarantee that understanding the process is going to be a ton easier than trying to memorize, well, 1, 2, 3, 4, 5 equations, okay? So that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for vectors and the geometry of space in the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.